Every drop of water on Earth has a story that may reach billions of years into the past. And one of the most fascinating suspects is the ancient comet. But does comet water actually match the water covering our planet?
Chemically, both are HO.
But chemistry has another clue hidden inside the hydrogen atoms. And that clue may completely change the way we think about Earth's oceans. Because water is not simply water when you look at its isotopes.
This is the mystery of deuterium and hydrogen.
So where did Earth's enormous supply of water actually come from? To answer that, we have to travel back to the birth of the solar system. Today, Earth looks like a water world. But most of its water is not actually available for us to drink. Oceans cover roughly 71% of Earth's surface. Around 97% of Earth's water is saline. Most of the fresh water is locked away in ice and underground reservoirs. But chemically, what makes Earth's water special? At the basic level, it is still HO. Hydrogen, however, comes in different isotopic forms. The most important one here is called deuterium. Ordinary hydrogen has one proton, while deuterium has an extra neutron.
Now imagine water stored inside one of the solar system's oldest objects.
That object is a comet. Comets are mixtures of ice, dust, rock, and complex carbon-bearing material. Deep inside, water can remain frozen for billions of years. They preserve material from the early solar system. When the sun formed, this disk contained enormous amounts of dust and volatile material. Some of those particles eventually became comets. Many were pushed into the distant regions of the solar system. Occasionally, gravity sends one back toward the inner solar system. As sunlight heats the nucleus, its ice begins to turn directly into gas.
Water vapor streams away from the comet.
Around the nucleus, a huge cloud called the coma forms. Solar radiation and the solar wind help create its spectacular tail. Inside that cloud are molecules carrying chemical clues from the comet's past, including the ratio between deuterium and ordinary hydrogen.
Scientists can compare that ratio with water on Earth.
And this comparison is one of the most powerful clues we have. The result, however, is not a simple yes or no. Different comets show surprisingly different isotopic signatures.
Some are clearly different from Earth's ocean water.
So what exactly does D/H mean? It measures the relative abundance of deuterium compared with ordinary hydrogen. Earth's ocean water has a characteristic isotopic signature.
Scientists can measure a comet's signature using instruments on spacecraft or telescopes.
Mass spectrometry can distinguish molecules with different isotopic compositions. The measurements can then be compared with terrestrial water. Many measured comets have more deuterium relative to hydrogen than Earth's oceans. That makes a simple comet-only explanation difficult.
But then scientists discovered something much more interesting.
Some comets have isotopic ratios much closer to Earth's water.
One famous example is Comet Hartley 2. Measurements from the Herschel Space Observatory found a remarkably Earth-like D/H ratio. Its water was much closer to the isotopic composition of Earth's oceans. That revived the idea that at least some comets could have contributed water.
But Hartley 2 was not the end of the story.
Later measurements of Comet 67P produced a very different result. Its water had a deuterium-to-hydrogen ratio about 3 times that of Earth's ocean water.
That is a major mismatch.
And it tells us comets are not chemically identical.
Their origins, histories, and formation environments matter.
Early Earth was a very different world. During planetary formation, countless bodies collided with the growing planet. Some of those bodies contained water and other volatile compounds.
Impacts could have delivered additional volatile material. But delivery from space was only part of the story.
Earth itself also contained hydrogen and oxygen-bearing materials. Volcanic and geological processes helped move water between Earth's interior, atmosphere, and surface. Over geological time, liquid water accumulated at the surface. The result became the ocean system we recognize today. So the real question may not be which single object delivered Earth's water. Another group of objects deserves our attention: water-rich asteroids. Some primitive asteroids contain hydrated minerals and water-bearing material. Their isotopic signatures can sometimes fit Earth's water better than many comets. This supports a more complicated origin story. Earth's water may have come from a mixture of sources. Comets, asteroids, and material already incorporated into Earth may all have contributed.
Think of it as a cosmic puzzle, rather than a single delivery.
Scientists use isotopes to determine which pieces fit.
And every new measurement can change our understanding.
Because the solar system still contains clues from its earliest days.
Now let's compare them directly.
On Earth, water is overwhelmingly liquid at the surface. On a cold comet far from the Sun, water is primarily frozen. Near the Sun, that ice can transform directly into vapor. Earth has a global water cycle powered by sunlight and gravity. Evaporation, condensation, precipitation, rivers and oceans constantly recycle water.
A comet's water behaves very differently.
At the molecular level, however, both contain HGO.
The key difference is not simply the molecule itself.
It is also the isotopic fingerprint carried by that water.
First, not every comet has the same kind of water. Their isotopic signatures vary significantly.
Second, some comets can resemble Earth's water more closely than others.
Hartley 2 is one of the most famous examples.
Third, comets may not be the only important suppliers.
Water-rich asteroid material may also have played a major role. The origin of Earth's water is probably a story involving multiple sources, and scientists are still testing exactly how much each source contributed. That means the water in your glass may carry a history far older than humanity. Its atoms may have passed through environments that existed before Earth itself.
So, is comet water the same as Earth's water?
The answer is not always.
Some comet water has an isotopic signature close to Earth's, while other comets are dramatically different.
The strongest evidence points toward a complex mixture of sources, rather than one cosmic delivery truck.
And every drop reminds us that Earth's water may be one of the oldest stories in the solar system. If you want